Good evening. I'm Ferry Aliabadi, and I have the pleasure of chairing this session of inaugural lecture by Professor Zahra Sharif Khodaei. But before we get to that, I've been given this form to tell you about the emergency fire briefing. In event of a fire alarm, please follow the emergency door, and you have to get. Okay. So follow the exit sign from the lecture hall, and you have to, at the assembly point, which is on the corner of the exhibition road at Imperial College Road. I've been at Imperial for 20 years, so I should know that. I shouldn't have to read it. Anyway, I'd like to welcome you all to this inaugural lecture. We also have many delegates online, so it's a hybrid meeting. After the lecture, you will have a chance to ask one or two questions, but that would depend on how long Zahra takes to finish the lecture. But that would be an opportunity. And we will follow with a vote of thanks after that, and we'll close, and there is a reception outside, so you have an opportunity to have drinks. Just a brief introduction to Zahra for those of you who don't know her. She finished high school in Iran, and she went to Czech Republic. She studied civil engineering at the Czech Technical University. She did her undergraduate, postgraduate, and PhD there, and in civil engineering. And like all good civil engineers, she joined aeronautics. She joined our department in 2009, initially as a research associate, and followed that by being a lecturer in 2014, and subsequently she got promoted until 2022. She became a professor. So this inaugural lecture has been waiting for a few years, and I think at the end of her lecture, you will get an idea of why that is. So, Zahra, over to you.
Thank you very much, Ferry, for your kind introduction, and thank you everyone for being here. Also, for everyone who is joining online, because I know that there were several people, including my parents, who couldn't be here in person. So, let me just start with my presentation. You've already heard the title. What I hope to introduce to you today about my research is to introduce smart aerospace vehicles. Now, before I get into the technical details, let me give you a little bit of motivation and background of what is it that I'm trying to address in my research and how I like to introduce that to you. So to start with, what are the main challenges that we are facing in aeronautics? And specifically, I put 2050 challenges because it's directly related to sustainability. We all know about the environmental impact. We know that it's a real issue, and we need to actually address it to try to slow it down. What is the issue of sustainability? We know that Europe has an ambitious goal of decarbonization by 2050. To be able to reach that for aviation sector, we don't need only to address, for example, alternative fuels, but we need to also address all aspects of flight. This goes from the design and manufacturing of aircraft to maintenance and operation and the decommissioning, so the end of life. So we need to address all stages of this to be able to have a much more sustainable flight in the future. Now, the other aspect is what does the future of flight look for us? It's not just, taking a plane and going from one country to another country. I don't know which one of you are young enough to remember the Jetson cartoon, but that's the futuristic look of what you want your cities to be. You want to be able to have flying taxis. You want to be able to get your deliveries with drones to your doorstep. These are ideas that are being developed at the moment, but we don't really see them being applied. And one of the main issues for that is safety. Safety over urban areas is really important because people need to feel safe having cars flying, and that goes to really the urban air mobility. And you see in movies and in cartoons how easy it is to maneuver cars about cities, but the air traffic management of that is a real nightmare. So that's another challenge that we need to address. We also have a lot of airplanes that are flying at the moment. What do we do when they come to end of life? Can we recycle them? Can we actually manage them better? When we talk about aircraft, we say fleet of aircraft. That means like if you look at Airbus A320, for example, they all been designed for a 30 years of service life. That's just an example. That means that all of them, it doesn't matter what route they fly, they retire after 30 years. But wouldn't it be better if we have a better idea of what is really the real operational conditions of the aircraft so we can optimize it? What if it doesn't go through high turbulence? What if it doesn't go through a harsh operational and environmental condition? Can we extend that to 35 years so we don't have to recycle or decommission it early? So that comes to maintenance and aging of aircraft fleet. And then I can go on about other advanced materials. We want to manufacture lightweight structures, so we're looking at 3D manufacturing and additive manufacturing, which has other challenges because if it's a new material, we need to do a lot of tests to get it right, so we have a lot of scrap. We also are looking into technology and innovation, so everything is becoming automated and digitized. It's the area of data, connectivity. How do we make smart cars, we make smart fridges, we want smartphones, we want to have smart aircraft as well. So how do we do that? We want to have everything automated, but of course, if we have artificial intelligence and automation include, we have much better, maybe sustainability, maybe better product, but we need to also address the issues of safety as well. So is it acceptable for public to have a product which is designed with artificial intelligence? So there is also regulatory issues that we need to address. And then is the space development. Everyone likes to go to space, not just for exploration purposes, but we also like to have space tourism. So we want to have launchers that are reusable, so it makes it cheaper for space travel. So not only the really top, wealthiest people in the world can go to space, but we want to have it accessible. So these are all the ongoing, I would say, interesting challenges that we want to face. And what is it that I'm proposing to address these challenges? And my idea is that we need to look at digitization. We need to have a smart aerospace vehicle. I call it aerospace vehicle because it doesn't necessarily have to be an aircraft. It can be a spacecraft, it can be a drone, it can be any other type of vehicle. We're looking at vertical takeoff and landing. We are looking at hybrid electric aircraft, hydrogen fueled, and so on. So we need to be able to address all these issues. What does a smart aircraft mean? So this concept actually refers to using advanced digital technologies throughout the life cycle of an aircraft. What do we mean by life cycle? So at the moment, we have the design of an aircraft, we have the manufacturing of it, and then the operation and maintenance of it. There is some data transfer between all these stages, but it's not necessarily fully integrated. But if we were able to have sensors which are distributed over the structure at all stages, from manufacturing, including design, manufacturing, and operation, we can try to optimize all these stages by using the data that comes from these sensors, combined with advanced analytics, machine learning, and so on. So this is an integrated health management approach for aircraft, which includes including sensors from the manufacturing stage during the operation, developing advanced analytical models that you can do processing of data, and so on. And you can then have a fully integrated structure, which is smart, and you can have data which is transferred between all these stages. So if I separate it into different stages, we have during manufacturing, which we call it process monitoring, and then during operation, which is called health and usage monitoring. And then what we want to do is we want to also do the prognosis. So we want to know what is the extended life or the safe life of an aircraft. So It's a lot of things to cover, but I'm going to focus on just the aspect of health monitoring and end-of-life assessment because of the timing and not to bore you too much with the details. Okay, I'm just going to stay here because I don't see the screen there, so it's difficult for me to follow. So what is this concept of smart aircraft? First of all, if I'm going to address the maintenance and operation, let's see what is the traditional maintenance. So how do we know if a structure is damaged or not? The oldest method that we use, one of the oldest methods, is a tap test. So if I tap a structure, I can listen to it and see if it's damaged. I have an example here where I have two identical cups. One of them has a crack and one of them doesn't. And I want you to listen carefully. Do you hear the difference? Obviously, the first one is cracked because it has a different sound. So this is one of the ways that you can do the damage detection during maintenance. Of course, it's very cheap, it's easy. You don't need very sophisticated equipment, but what are the problems with this method is that you need access to each part. You need to ground the plane during maintenance to do this check. You need to send a technician, and you need to rely on the qualification of that technician to be able to make that distinguish between the sounds. So it's not, I would say, the optimum way to do the maintenance of a structure. So what we're proposing here is that rather than having to do this manually, we can do this automated based on sensors that are integrated within the structure. So the way to make the maintenance smart, we can follow the concept of human health. If I cut my hand, the neuron sends a signal to my brain, and I know that, oh, I feel pain, so I need to investigate more. I check the cut. Am I bleeding a lot? Can I just put a plaster on it, or I need to go to the doctor? So I do a diagnosis and a prognosis. We want to do the same for a smart aircraft structure. So we want to integrate sensors, and this is the concept of structural health monitoring, which is an alternative way to non-destructive inspection. And we want to rely on the information that purely comes from the sensors. We can automatically excite the structure to acquire this data, do some processing, and then say whether there is damage in the structure or not. And then the advantages are much more because we don't rely on human interaction with actual damage to know what sort of maintenance that they need to do further. And we also don't need to ground the plane and have access to the part. So you can see here as an example, I can put these sensors attached to the surface of a structure and excite it with given wave. And it works exactly the same as the tap test, where as the wave is propagating, it interacts with the damage. And if you can pick up these signatures, you're able to identify whether the structure is damaged or not. But of course, it sounds very nice. How do we design such a system? How do we implement it and test it in real structure? So this is what we want to achieve with the real-time health and usage monitoring. I put there health and usage monitoring because health monitoring is during the maintenance. I want to know whether the structure is safe to fly. And usage monitoring is related to how the structure is operated. So I want to make the best extended life of the structure. So I want to know what are the loads that the structure is experiencing. And I can have those information coming from the sensors as well. So what we're proposing here is that we're going to integrate the structure with lots of sensors. This structure for us is aircraft, and we want to gather this data continuously as the aircraft is flying. In the first instance, I want to have a system which will give me early warning. So it tells me, oh, something has happened, go and check. I can then do the second phase, which is the diagnosis, further diagnosis. I know what is the sort of damage, what type of damage is it? Is it extensive? Do I need to take an action, further action? And that's where we go to prognosis. If we have a digital twin developed, we can say that actually, what would be the prognosis if the structure has this damage? Can it still fly, or we need to ground the plane and we need to repair it immediately? So it all sounds very easy, but of course it's easy to demonstrate it for a simple structure in the lab, but how do we apply such a concept to an aircraft? Aircraft structures are very complex, and there are a lot of regulations. So how do we go from this concept to reality? So the first thing to address is that, okay, what type of sensor do I use, and where do I place them, how do I attach it to the structure, and so on, and how do I gather data? So this is where we come to the first issue, because airspace structures are weight sensitive. So I cannot offer you a solution and say, well, you can have a much better safety of a structure that is flying, but it's going to add 300 extra kilos to a small part. You can see here a picture of a small, is a wing box panel which has been sensorized with piezoelectric transducers. These are these sort of transducers where you can use them as actuator and sensor. They're very small, they're very light. You can bond them to the surface of a structure and excite it with some guided waves. But you can see the wiring issues. There's a lot of wires coming. They're heavy, and they can break the terminals of your sensors. And what is underneath there, that big box, is the data acquisition unit. So this is a lot to include on board of a structure. So what is the solution to that? What we have developed is we've developed a flexible layer where you can integrate your sensors on it. You can have the wires printed on this. So you can do this with an inkjet printer. And this way, you can have flexibility. You can reduce the weight of the wires. And you also have an adhesive film where if you bond this with heat to the surface of your structure, you can then also with heat remove it. That gives us the repairability. So if the sensor is broken, we can easily remove it and repair it, because that's also what we need to think about. We cannot have sensors permanently mounted on the structure without having the possibility to repair it. And then what do we do with the data acquisition? We also developed a miniaturized solution. So this is the box that you can see here. We can have up to 24 sensors attached to this. You can acquire the data. It has a microprocessing unit, so it can do some processing of the data for you. And then it can send the data through wireless transmission to your computer. So if you're the operator, you can gather the data and then process it. So this is how we dealt with the first issue, which is, OK, we needed to be a system which is, in reality, possible to integrate with our structure, and it's weight sensitive. This is an example that you can see is a fuselage barrel made of composite. And in all these bays here, we have integrated 4 sensors with the same design as you see here. And you hardly see any wires that are coming out. We see the connectors at the end. So that's how we dealt with the issue of weight for a real structure. The second issue is, if I want to have a system especially for health monitoring of my structure, it needs to be reliable. The sensors have to survive the operational and environmental condition of the main structure. So for us, an aircraft flies even just in Europe, going from one country to another country, which is mild condition. It goes through something like minus 40 degrees to plus 85 degrees. So if I have sensors attached to my structure and the structure goes under, are exposed to this temperature fluctuation, it also has to survive that, as well as mechanical load that the structure is exposed. So the way that we have addressed that is we've done quite a lot of tests on all components that remain on board. These are sensors, the bonding, the wires, the connectors, the printed tracks, to demonstrate that they can actually survive the operational environmental condition and also operate reliably after that. So here you see some examples of different bonding technique, which they are exposed to a combination of temperature and mechanical load. And you see, for example, the first one, you see a lot of fluctuation after each test. This is not acceptable. Second one as well. But there is this solution, which is what you see here, is this film for bonding. And that's an acceptable solution because it still gives me reliable result after undergoing these conditions. So that's to do with hardware. Second question is, OK, I have my sensors. I have my unit that can gather the data. What is it that I want to record, and what alert I want to give to the operator? Now, We are moving from metallic structure to composite structure because they're more lightweight and they are, have better strength to weight ratio. The manufacturing of them is also different. We can combine a lot of matrix and fibers and so on. So I don't want to go into details of composite, but they're better than metal for some applications in aeronautics. But the problem they have is that if they're exposed to an impact, you can get damages that is difficult to detect. An impact can be any hit from an external object. We don't know when this can happen. It can happen at any time, so we cannot plan for it. So the idea is that these sensors can record these impact events. Now you might say, oh, but does this happen really that often that it's a threat and we need to record? And the answer is yes. This is here a map that you can see is a probability map of having impacts on aircraft at different locations. This is from Airbus. And you can see there are areas, especially surrounding the passenger door, that has the highest possibility of having impacts. So it happens a lot. But of course, we're not interested in every type of impact. We want to detect impacts that are threatening to our main structure. Then what are the scenarios of impact? So what are these sort of impacts that we're talking about? Because they can have different energies, different mass and velocities. So this is also another map which shows you that different parts of an aircraft are prone to different types of impact. We're talking about bird strike, hail. We're talking about tool drop. Ironically, a lot of damages that happens to composite structure is during maintenance of aircraft, and it can happen just from a technician dropping the toolbox or a hammer from waist high. And obviously, they will not report it. So it can go undetected, and it can be dangerous. There are other sorts of impact that we don't need sensors to detect. This is an example of a bird strike. We don't want sensors to detect that. That's very obvious. But there are other sorts of impact where, as you can see here, this is a composite plate, and it has been impacted where on the surface, if you look very closely, you might see some fiber breakage. But if we do a C-scan of this, there is a significant damage through thickness. And this is extremely difficult to detect unless we really take that part out and we do a C-scan or really complex monitoring systems. So what is the difference between metallic structure is you see here an example of a metallic wing which has been exposed to impact, hail impact. You see all these dents is very visible. But for composite, we do not have that visual inspection option. So this means that we require more complex methods to inspect damage in composite, as well as we require higher safety margins because we design a composite aircraft knowing that we're not going to be able to detect these sorts of damages. So it's supposed to fly with those damages, so we make the design conservative, and it can be heavy. So if we want to have lighter structure, we want to be able to detect that. So that's why we want to detect impact. Now, what are these impacts that happen to the structure? What are the responses that generates, and what are the signals that we record? This is a simulation of a wing box, and there's an impact that is happening in this location. It generates some stress waves or strain waves that travel through. If I had a sensor, a piezoelectric sensor, as you see here, these are able to record as a voltage output these strain or stress waves. Now, if I have a number of sensor networks, so distributed over the structure, I can record all these sensor signals. Now, what I can do with these sensor signals is I can actually use the information recorded by this to know where is the location of impact and also know what is the magnitude of this impact. And based on that, I can do my diagnosis. Now, how do I do that? How do I go from these sensor signals? Well, OK, that's a little bit more complicated. For a very simple structure, we can use physics-based methods because we know that there are parameters that physically relates my strain-induced wave to location and amplitude. But for more complex structures, of course, we resort to machine learning and artificial intelligence. So an example is we can use either an artificial neural network or a convolution neural network. But what we give it as an input to this we don't use it as a black box approach. What we do is we give it some features extracted from these signals, and as an output, we want to get the location of impact and also the amplitude of this impact. So these two examples here gives us very nicely the location of impact. We can also do the same for amplitude. Now, how do I know whether this impact was high enough that could cause damage in my structure? Is by detecting the amplitude of that force. So how do I show you convincingly that the amplitude of the signal is also related to the force is through a simple experiment. We have manufactured 4 identical plates. They all have 1 sensors attached. We put this in an impact tower, which is an experiment where it's very controlled. You can measure the force. You know exactly the energy. So you can increase the energy gradually. This is the contact force that has been recorded by the impactor. So the impactor itself is a steel ball, which has a piezoelectric cell in it. So you can measure the force at the location of impact. And you can see that as this force increases, you get damage that is initiated in your structure. Now, I can clearly, through a physics-based method, there are equations for composite that I can actually detect what is this threshold for damage initiation. But in a real structure, I don't know what is the amplitude of the force. All I have is my sensor signals that are recorded. So what I try to do is then relate the amplitude of these sensor signals that record the impact event to a threshold, which is initiation of damage. And I can do this through experiments, through physics, through machine learning, and so on. So there's a lot of ways that we can do that. And once I know this threshold, which above this is going to be threat to my structure, then I can have an alerting system to say, OK, this impact was damaging to the structure, and so on. So that's how I would do it. Now, we've developed, of course, with our students, a prototype. And for the sake of time, we were going to watch the video rather than doing a live demonstration. But this is basically the unit that we have here. There's a plate with sensors attached. And what you will see here in this video is, as we will have real impacts happening on this plate, you will see the sensor signals that are recorded with our unit. And here is the live prediction. So it takes a couple of seconds from the impact event compared to where you see the predicted location here. So you can see it nicely predicts the location. The algorithm is based on machine learning. So it obviously means the more data you can have a better detectability. And the dashed line here gives you the confidence interval. It means how confident are you that this is the exact location of damage. And obviously, like other statistical-based approach, you can include Bayesian updating or Kalman filter to try to have a better estimation as more data becomes available. So this is just in a simple way to show a demonstration of putting the technology and methodology together. We have actually tested this on a much larger fuselage panel, and it works very nicely. Now, the other aspect is, OK, now I know that there is damage. Sorry, I know there is impact, and it's threatening. So what are the implications of this impact? What is the damage that has been generated? Do I really need to repair it? Or I can still have, I don't know, 2 or 3 more flights. So we need to characterize the damage further. That's where we go to active sensing. And as you see here, I will play the video again. This is a plate. We have sensors, again, surface mounted there, and is exciting the plate with a waveform. And this wave is propagating through the plate. And you will see how it changes the propagation at this location, because internally there is damage. Now, this is experimental measurements that has been taken with laser Doppler vibrometer, which is a 3D LDV setup, has 3 laser cameras, and you point it at one location, and you can record the strain or the displacements in 3 axes, in X, Y, and Z, so you can get a very nice plot like this. But this is not the structural health monitoring that we're talking about, because this takes very long time. You need real access to the part, so it's not just by using sensors. We use the sensors to excite the structure, but we recorded this this is how we excite the structure with sensors with these guided waves. But in reality, we want to capture the effect of damage on the guided wave, but not through all the plate, because we cannot do that. We can only record it for this path, from actuator to sensor. And it looks something like this. So I know that the wave has propagated. Now, I don't know anything at this stage unless I have a baseline. What it means is that I take the recording when I know the structure doesn't have damage, and I save this as my baseline. So at the beginning of the service life, I have manufactured it, I have scanned it, and I know there is no damage. I take a recording, that's my baseline. After a while, there's the possibility that there is damage. I take my recording again, then I know that if I compare these two signals together, there's a difference. And I hope that that difference just comes from damage and from nothing else. And I can use this to detect damage. Of course, in an ideal scenario, this difference only comes from damage. But in reality, it's not the case. We have a lot of variability, noise in the system that will alter this comparison. So if we have, again, a network of sensors, what we will get is we want to define an index. We want to define a parameter which automatically detects damage for us. I don't want to sit there and reduce these two signals from each other and say, oh, actually, it looks like there is something. No, I want to develop a system which automatically does that. So I develop a damage metric. And how it looks like for a network of sensors, when there is no damage, you still get some changes. So this is comparing two states to each other and coming up with a damage index. And hopefully, when I have damage, I can identify that only the highest values for the sensors that are close to damage gives me the location of damage. Again, this works very nicely for a plate which we test in the lab. But when it comes to real structure, the question is we have to develop a damage index which is robust and reliable. But again, how do we establish this threshold for damage? Because I said always when I compare state A with state B, I will always get some differences between the two. How do I know that this difference above a certain threshold means that there is damage in the structure? So this is the challenge that we face. How we dealt with that is for very large structures, we developed, first of all, measurement over an extended period by simulating different operational environmental conditions. So putting this in an environmental chamber, changing the temperature, and so on. Of course, hardworking postdocs and students had to do all of this. But also including uncertainty. We have uncertainty in the placement of sensors. We assume that we have uncertainty in knowing the temperature, in knowing, for example, the humidity and the operational conditions. So we look at this from statistical point of view to be able to see all this variability in the data when there is no damage, because we want to have a very robust threshold for detectability. And by doing that, we can populate our database with a lot of scenarios, and we define our statistical threshold based on this. Now, again, without going through too much detail, then when we have a real damage scenario, we have outliers. So this would give me my statistical threshold, and the states that are clearly outside this threshold, I can then say with certainty that there is damage related to these scenarios. And again, once we have detected damage, we can take it even a step further and we can localize this damage. So the last step of this puzzle is what do we do then next? So I detected there's a threat. I know there is my damage. I can localize it and say something about its severity. So what is the prognosis? This means how much is the remaining useful life of my structure? Can I still fly? Or I need to repair it and ground the structure. So this is what action I need to take. This is where we go to digital twin development. The first question is, if I know that the structure has damage, I need to be able to answer how much my strength is reduced because of this damage being present. How do I do that? Now, in a lab, it's very easy. If I want to know what's the strength of this coupon or specimen, I pull it and I break it. Then I know what's its tensile strength. So that is a destructive test. But for real structure, complex structure, I want to know the failure load, but I want to know what's the failure load when I have a damage on it. So what we do is we do this experiment twice. Once when there is no damage, I record the load. Once when there is damage, I record the load. I look how much it has reduced, and that's the reduction in strength. It's easy to do it for coupons, but what do you do when you have a stiffened panel made of composite? Well, you still have to, this has been done, is a normal practice. You test this for the worst case scenario and you record it. But I want to have a system for an aircraft, for every part of aircraft. You cannot really test every part. So that's where we combine it with numerical simulation. We try to estimate the effect of damage, which we have detected from our sensor system, and then include that effect in our numerical simulation through machine learning, for example, Gaussian processes and so on, to estimate the damage effect, and then be able to say that for any damage area, I'm able to tell you how much the strength has been reduced. So this requires quite a lot of implementation and progress in it. So this is just to introduce you the topic of my research, and I just very quickly go through a few slides to show you what implementation and use cases there are. So the first, I would say, most noticeable implementation is through this Sherlock project, which was a Clean Sky core partnership, where we've developed structural health monitoring techniques for 5 main structural items for a regional aircraft, all of them made of composite, each with different manufacturing technology and different material, just to showcase that we have to tailor this system for every type of manufacturing and every type of structural complexity. So we've looked at 5-meter curved fuselage panel. We looked at window frames, fittings, and bulkhead pressure joint, all made of composite, and try to integrate SHM systems to be able to monitor and detect the integrity of these structures. And at the end of the project, that 5-meter fuselage panel was tested as well. So this just shows you the size of the test. The other ongoing project that we have is about developing digital twin, but this is more about usage monitoring. So what we have is, as an example, we have a physical structure, which is, if I go back again, which is under load, and I want to be able to use sensor data to say what are the actual stresses or strains that the structure is exposed to in real time or near real time. So that requires quite a lot of development from hardware side, and also looking at data processing at cloud level to speed the process up, and also doing, for example, some advanced analytics that is very fast, and we can detect what is the state of the structure as the structure is under operation. And in the project, we're going to test this, or we are developing it for a drone, which has composite wings, as well as for metallic aircraft. And at the end, we're going to develop a visualization platform which shows you really nicely this digital twin model. The other application which we are also looking at is for space application, and mainly for reusability in space. Because what happens with every launch is you go through different stages. You go through launch, ascent, orbit, descent, and then landing. And each of these stages have different complexities in the operational and environmental condition. What we want to know is that if this launcher has landed, can I take this for another mission? Or I need to really test it destructively again and go through the certification. So we are applying structural health monitoring systems to these launchers to see whether I can assess the integrity of the structure using sensor data that are integrated, and then say, if it's okay, I can go for another mission, and then a second mission, and so on. So every time the structure lands, I'll do the assessment, and I would say whether it's possible to fly again or not. The other thing is there's a threat of impact for space structures as well, but what is this threat? We have sent a lot of things to space, and as a result, currently we have more than 23,000 pieces of space debris that are flying around. And this is a threat for existing space structures or for launchers. So we want to, we'll show you an example here that this is an arm of here's a robot in space. And what happens if there's a space debris that has been impacted there? You can have severe damage in the structure. But you want to know actually this remotely to be able to detect this. You don't want to send an astronaut there to check it. So you want to have sensors on the structure that is able to give you this information. So we've done some integration of sensors within the space structures, both in the shield and in the main structure, and we are trying to use the information from the sensors to characterize the damage. But of course, when we talk about impact in space, these are hypervelocity impacts. These are not low velocity impacts that we have in for aircraft application. In those velocities, what happens is that you can actually shatter the projectile into lots of pieces. So it generates something we call debris cloud. So you don't have just one point of impact. But if this debris cloud hits your main structure, you have a combination of damage in lots of locations. So to understand that, we have done some modeling, because experimentally it's very difficult and expensive to do this hypervelocities impact. So we are looking at modeling these stress waves that are generated in the structure and use this information to characterize the impact events. So these were some of the projects that currently we're working on. Just to, again, now summarize the technical part of my talk, the future research direction, really, if I want to summarize it in one slide, would be the digital twinning. We are developing hardwares, we are gathering data, we are also looking into modeling as well, but really what is the future is being able to develop a digital twin which can replicate the real structure in service, so that we can have information as the structure is under operation of its state, and also be able to predict that further. What that means is that we need to do advancement in data analytics, in the hardware, and not just in the hardware for acquisition, but also for processing of the data as well. So that concludes my technical part of the talk. And of course, I will have to thank many people. You've seen some of the work that we are doing, but of course, there's a team behind it. First, I'd like to thank my PhD advisors, because they got me into aeronautics. As you heard, I come from civil engineering background. I did my PhD at Czech Technical University under the supervision of Professor Jan Zeman and Peter Prochaska. And I did my PhD in numerical modeling, so specifically boundary element modeling. And that got me into aeronautics, so I need to thank them. And as well as, I think, all aspects of my research and my progress, I need to thank my mentor and my colleague, and I think I can say my friend as well, Ferry, for his support. He really pushed me where I didn't believe in myself, and he really encouraged me to have this wonderful academic and research life. So I really need to say thank you to him. And of course, all the colleagues in the department, not just the academics, but the technical staff as well, and also the admin staff who support everything we do on a daily basis. And also to all of you for coming today. I know that there are a lot of ex-PhD students and postdocs and colleagues who are joined online, so I know I don't see you, but I'd like to say thank you for your support in all these years as well. And at the end, the most important, I'd like to thank my family. Specifically, I'd like to thank my parents. They cannot be here, but I know that it meant a lot to them to be here. As you heard, I'm from Iran, so at the moment it's not very easy to travel. My dad is also an academic, so he taught me the love for science and the passion for it. My mom is one of the kindest people I've met in my life, so she taught me to be kind, but also to believe in myself and stand up for myself. So thanks to them, and my sisters have always been supportive. I need to thank my partner, Shelton, who's at the moment, I think, is on babysitting duty. So he has supported me all these years, as well as his family. So I need to thank them as well. And at the end, I have to say thank you to my daughter, Mina. She has truly given me a different perspective to life, and what this means for professionally and personally as well. Professionally, I would say I had never imagined how hard your career will be when you have a child. and specifically if you're a mother, because I know that these days you share parental duties equally with fathers, and otherwise nothing is possible. But there's always an aspect of you sacrificing your time for work, not because you have to, but of course you want to, but it just makes it a lot more challenging. So when I became the first female professor in the history of the department, I thought, wow, that was such a great achievement. But if I reflect on that today, I didn't have my daughter at the time. I would say I like to celebrate the first female professor who's a mother and gets to that achievement. So I think that we need to really do our best to get that, because we have several mothers who are not professors yet in the department. So I like to see that happen. And again, I like to dedicate everything that I've done or achieved so far to all the girls out there who don't dare to dream. Because I came from Iran, where I never dreamed of being a professor at Imperial College. I never dared to dream that. I thought it was never even on the cards for me. So in a way, I was lucky that I was in the right place at the right time, that I got to Imperial. And then, of course, I worked hard. But I want to say that I want everyone to dare to dream, because it's possible even when you think it's not possible. So thank you very much.
Okay. Thanks very much, Zahra. Before I open the questions, as Zahra said, we are all proud that she's the first female professor in the department. And I know that many of our undergraduates and PhD female students, they always tell me that how much they look up to her and how much she is encouragement. But I also noticed today, Zahra, another first. With Zahra, we go to a lot of colleges, does the presentation. And I noticed today is the first time she finished on time.
I noticed too.
So you achieved that as well. So now I'd like to open the talk to questions that you may have initially from people in person, then we go online. So are there any questions? Yes, please.
You concentrated for most of the presentation on impact damage. I just wondered, can your systems also be applied to gradual stress damage? And is it feasible for the approach to be used for the interior of aero engines?
Yes, you're completely right. I focused on impact damage, but we can easily use it. It's much easier, actually, to use it for damage in metallics, like fatigue damage, because the signals you get from initiating fatigue and the interaction with a crack is much easier to spot than damage in composite. That's why my talk was more concentrated on impact in composite, because that's more challenging. But I think that in some aspect, they do use some sort of sensorization in the engines at the moment, and they do structural health monitoring of aero engines. So that's already applicable. Yeah, so there's a lot of also work in progress in having different types of sensors. So yeah, the short answer is yes, you can detect degradation. It's more challenging, again, if it's in composite, because degradation in composite under fatigue specifically is not easy to detect. If you have an impact damage, it's clear sort of signature that you get. Yeah. But yes, yeah, it's possible.
Thank you.
Other questions? Yes?
Regarding, thanks for very interesting talk, but I have the questions concerning composite materials. There are many, failures, not only mechanical, but also chemical contamination, not only by water, but chemical fluids, skydroll, for example, thermal degradation, curing, yes, etc. So how many parameters did you consider in one task using signal processing? Because I think that this challenge that is not so easy.
Yes.
Yeah, and
yeah, thank you. That's a very good question. So I would say the most extended one that we looked was specifically For impact, but under so impact type of damage, but under operational and environmental condition, which includes temperature and humidity. So we did not include any chemical effect. But we have, at the moment, we have a project, an ATI project with Rolls-Royce, and I think I didn't put it up there, with University of Bristol and NCC, which is looking into degradation of hydrogen storage tank. And for that, of course, it depends on the tank if you have a liner or not, but then you need to include other aspects, which is really from overpressurization under fatigue loading, to see what are the parameters that you can detect. But specifically, we have not looked into chemicals. Yeah.
Any
That's
other
a question
questions?
from Mina.
Yes? Okay. Please, there. Yeah, yeah.
Hi.
I think Mina has a question.
I
later.
know. When do you finish?
It's on, okay.
Yeah.
Hi, okay, thank you for very nice presentations. And I think my questions is about whether the deployment of the method in a full-scale system will be limited by the amount of data. Because as far as I know, I think for a long-haul flights, the sensor data collected by an aircraft amounts to 2 terabytes, and I think processing the data, especially for real-time decision-making, will be challenging. So, yeah, so whether it is a limitations, and if it is, what are the mitigation?
Thank you. That's a very important and good question that you asked. Yes, you're completely right. So one of the aspects of the technological development we've done with the system is that it's modular. So that's why we talk about sensor nodes. So we have one module that you can have 24 sensors connected to it, and then you have another module. So that deals with the large structures and the number of sensors that you can record, attach to one module. But of course, then there's the question of how long can you record data. So for our passive system, to deal with that, we have actually developed it to have 2 modes. So it's a sleep mode and a wake-up mode, because we actually don't want to record when the structure is not impacted. So it has a comparator, which compares in the background, but is running on very low power. So it records when an actual impact event happens above a certain threshold. Then saves that data, and because it has a microcontroller, you can actually use algorithms to backtrack and get the actual time that it happened, because even though you have systems where they wake up very fast, you always lose a little bit of data. But we've tested that, and that part is not a problem. Now, again, that's for, I would say, for one type of sensor, which is passive, in this case, recording impact event. In the other project, we have Avatar that I briefly mentioned. What we are trying to record during flight is the strain data from strain gauges, also acceleration, temperature, and so on. And there we have large number of data. So the way that we have solved that solution is that we have a hardware that has a microcontroller and does some processing, but then everything that we are developing is cloud compatible, because then we send the data to a gateway, and this gateway is connected to cloud. So as the streams of data come in, we then process the data, and you can apply compression, decompression algorithms on it to reduce the size, or do feature extraction. If you know that you only want certain features of it, you can do the processing on board, but then you only send the information then to the gateway, and that gets stored to cloud, because we're working with partners who are developing actually infrastructures for cloud-based solution and telecommunication. So they're implementing algorithms to make sure that it's possible to do this during flight.
Okay.
I was looking at your first slides there, where you're looking at air taxis over cities, and you're going to be at lower heights, lower velocities, lots more birds and lots more bird strikes. And have you looked at the impacts between birds and propellers and rotors on helicopters? And isn't that the greatest danger of all?
You're right. So if you're looking into or urban air mobility, where you have propeller type of aircraft, that's one of the threats. But that's the project that we are working on is looking at drones. So it's without a propeller. So we've tailored what we're developing for that. So I haven't looked actually into the impact of birds on propellers. But I understand that, yes, that is an important aspect that needs to be looked into if we are going to allow those vehicles to fly over urban areas, yeah.
Let's go to the delegates online. Are there questions?
Now, sorry, but because I don't know if these messages are being sent along with the video, I just want to first introduce some of the comments here. NUS says, thank you, Zahra, for being an incredible role model for us. Victor Yurkisius says, great job, Zahra. Emilia Tang, proud of you. Ali Mehman Parast, well done, Zahra, very inspirational talk. Sadi, congratulations again, excellent talk. And Jan Zeman remarks how much of a proud academic father he is. So after this pose to the question, Matthew Clathworthy says, thank you, Zahra, for an excellent presentation. I have a question. How well do these HMUs deal with lightning strikes?
Okay, so the lightning strike is a challenge because usually when it hits the aircraft, it actually can take all the sensors and the connectors as well. So it would depend really to the extent of damage that the lightning strike has caused. But of course, the type of damage that lightning strike causes is possible to be detected by these sort of sensors. So the only thing you need to ensure is that your system is shielded and secured from this lightning strike. Otherwise, we've done actually some simulations on those type of damages. Not experimentally, but through simulation, and you have a very clear signature in those damages. So with guided waves, you're able to detect and characterize them.
Okay, so Daniel Jagger asks, first of all says, awesome lecture, looks like the field has grown leaps from your work, and asks how well does the machine learning approach for impact localization cope with propagation speed properties in composite structures?
That's a very good question. So the issue there, just to tell to the audiences in the room, if you're not aware, is if there's an impact on a structure, if we know the velocity of the wave that is traveling through the structure, it's very easy to locate where the impact point is. It's like how you GPS pinpoints your location, because they send a signal, but they know the velocity of the signal. So from the time of arrival, you can get the distance. It's the same for impact, but the problem is that this velocity is usually frequency dependent. And when you have an external impact, you have multiple frequencies that are generated, so it's not a single one. Now, on top of that, you can have composite structures that are, have properties that are direction dependent. So in that way, it's not easy to know what is the velocity of the impact so that you can get the location. So if you use machine learning, it can learn what is the relationship between your time of arrival and with the location of impact. So in terms of impact localization, actually, it works very well with machine learning because the relationship is not that complicated for an intelligent machine to learn. So for impact locations in composite, if you even have an isotropic relationship of of the wave propagation velocity, it works quite well.
Okay, I think it's time. I'd like to draw this to end and ask for Professor Ostovic to give the vote of thanks.
Wiesław Ostachowicz.
Awesome.
Okay, I have, a letter from my research group. I'm from Gdańsk, Poland, so let me now give me the time to read the letter from my research group. Dear Zahra, on the occasion of your inaugural lecture, my warmest congratulations and best wishes for your health, satisfaction with your numerous life achievements and personal prosperity. Your years of hard work and deep commitment have contributed significantly to achieving the position you can now boast of as an outstanding professor and a scientist with an international reputation. You deserve great recognition, not only for your intellectual achievements, but also because of your diligence, modesty, kindness, and loyalty to your values, thanks to which every contact with you is extremely valuable. In times when the deficit of authorities has not spared the scientific community, these traits are hard to overestimate. I wish you continued fruitful scientific work and many years of health and satisfaction with that scientific activity brings.
Thank you.
Thank you very much. Thank you very much. Thank you very much. That's very kind of you.
Okay, so I'd like to bring this inaugural lecture to close and invite you to join us outside for drink reception. But before then, I'd like to thank again Zahra for an excellent lecture, and thank you very much.
Thank you.